Okay, so today's the last lecture. We'll do our last application of the homological theory of regular local rings. And I don't know who's out there who follows this course. So out there somewhere in the ether, maybe there are people. Next year, I was planning to teach a course on sheaves. So usually there's this homological algebra course, and then there's a second course about sheaves and cohomology. So I was going to teach it, and that's why I didn't do anything about that in this course. But I'm moving now to PhysTech next year. So someone else will be teaching the course, and I'll be teaching differential geometry at PhysTech. So if anyone is looking for a master's program and is interested, go ahead and write to me. Okay, so let's see. Last time we proved this theorem that a Noetherian local ring was regular if and only if it had finite homological dimension. And in the proof, I actually said something at the very end that was a bit incorrect. So I want to fix that. So last time, we proved that A was regular local if and only if the homological dimension of A, which we know for local ring is the projective dimension of the residue field, if and only if that was finite. And we needed, at the end of the proof, we needed to know that the depth of A, which is dimension of A, the curl dimension, we needed to know that this was, so we always know that that's less than or equal to the dimension of maximal ideal mod maximal ideal squared. That's true for any Noetherian local ring. So we needed the reverse inequality. We needed to know that this is greater than or equal to dimension of m mod m squared, which is what? The number of minimal generators of m. And by the Auslander-Buchsbaum formula, so this is what should have told us that there was a mistake somewhere, that we didn't use the Auslander-Buchsbaum formula. So by the Auslander-Buchsbaum formula, the depth equals the depth of A of the ring equals the depth of the module plus the projective dimension of the module if the projective dimension is finite. And so we're assuming finite homological dimension, the depth of K is 0 because everything in the maximal ideal acts trivially there. So by the Auslander-Buchsbaum formula, this is projective dimension of K. And we want to see that we have this inequality. We need to check this. And let me double check that, yes, the camera is on the screen. And what we did, we constructed, so given a minimal generating set, F1 through Fn of the maximal ideal M, so this is the number n, we looked at the Kazul complex on those. So we showed that the Kazul complex on that collection embedded into free minimal resolution of the residue field. And the proof of that involves studying it kind of at each level and showing it was a split injection there. And then I claimed, erroneously, that this actually split off as a complex. But if you looked at the argument, it worked for any local ring. We get this kind of embedding. And it's just not true in general that this is a summand here. So I claimed, so falsely claimed, that this is a summand for any local ring. It's just a summand at each level, but the splitting is not compatible with the differential. However, it doesn't matter. We're already done now. However, just having an embedding is enough to finish the proof. Because it shows that this, so the length of this complex is at least as long as it's as long, exactly as long as the number of minimal generators. So the top, so KF looks like the following. It's A, and then A plus N. So this is 0, 1. Then wedge 2, all the way up to wedge N. Okay, so it has length N. Therefore, whatever the length of F is, so the length of F, which is the projected dimension of K, is greater than or equal to N, since this embeds. It must be at least as big. And in fact, since we know so this is what we needed to check, and now we've checked it. And moreover, since we know the reverse inequality, the lengths of these two are actually equal, and this is an isomorphism. So the Kazul complex in this case is the minimal resolution. Okay, so that's fixing the proof from last time. It was there. I just made, at the very end, an erroneous claim and thought we were done. Okay. Okay, so that's from last time. And this time, so today, we want to show regular local rings are factorial. They're unique factorization domains. So we're going to study factoriality. And to prove what we want, we need some facts that are not very hard from commutative algebra, and also some facts which we may or may not have done already in the seminars. So I'm going to give a list of facts. Some of them are purely about commutative algebra. We can check some of those in the seminar. Some of them are more homological in flavor. I'll at least sketch them. and see how much time we have, and then whatever's left over we'll finish in the seminar. So facts we need. So first it's about, let me give a list of them so that we can refer to them. So let's suppose A is a Noetherian domain. Then A is factorial. It's a unique factorization domain. So remember what that means. It means they're irreducible elements. Irreducible means you can't factor them further unless it's a unit times something else. So every element should have a unique expression as a product of irreducibles up to a unit. So the only ambiguity is this modifying the irreducibles by units. And it turns out to be more convenient to work with prime elements instead of irreducible elements. So an element is prime if the principal ideal generated by it is prime. And in a unique factorization domain, prime is the same as irreducible, but in general they're different. So prime implies irreducible, but in general not conversely. But it turns out to be easier to state factoriality in terms of prime elements for what we want. So we say A is factorial if and only if every element is a product of prime elements. And the reason it's easier to state it like this is that checking uniqueness for factorizations is kind of difficult, but if you know that the elements are prime, the uniqueness will come for free. And B, a Noetherian domain. A is factorial. This is a little more abstract, and it's not that hard to prove. A is factorial if and only if every codimension 1 prime is principal. Okay, and this means, so codimension, remember, is, in this case, because it's the domain, it means that there's nothing in between 0 and this prime. There's no other prime in between 0 and this prime. Equivalently, if you localize at this prime, you'll get a one-dimensional local ring. C. So these are purely commutative algebra facts, which we can discuss in the seminar. Here are some homological facts, none of which are hard. So if A is finite homological dimension, not even necessarily local, just a commutative ring of finite homological dimension, then so is any localization. So for any multiplicative set, yes. The idea here is pretty simple. Take a module over the localization, restrict it to be a module over A. It has a finite length resolution there. Localize that resolution, it will give a finite resolution for this module. So you have to check that it works, but this is the idea. And yes. we need to know that suppose A is Noetherian, M a finitely generated module, then the following are equivalent. So I could ask for M to be projective. I could ask for the localization of M, P, to be free over the localization of the ring at P. This is for all P prime. And in fact, it's enough to do it at maximal ideals. That's sometimes more convenient. It's the same, but for all P maximal. And you can also rephrase this in another way, in terms of what's called locally free. So in terms of algebraic geometry, this is saying that on the spectrum of A, of a Noetherian ring, the projective modules correspond to their sections of vector bundles on the spectrum. You might know this fact from the study of manifolds. If you have a vector bundle on a manifold and you look at its sections as a module over the ring of functions, because the vector bundle is locally trivial, the module of sections will be locally a free module of rank equal to the rank of the bundle. And similar fact holds in algebraic geometry. Oh. Okay, and two more facts, and then we'll come back and prove some of them, but I want to get to the main point. Just list all the facts, prove the theorem, and then see how much time we have to check facts. But please, if a statement of a fact is unclear, ask me about it. Okay, so next fact is that if I have a module such that when I add on n minus 1 copies of A, my ring, I get something isomorphic to n copies of A, a free module, then M, in fact, is isomorphic to A. Put differently, suppose I have a module which is generated by n elements. So there's a surjection from here to here. And suppose it splits off in such a way that the complement is also free. Then of rank n minus 1, then I get that the module was actually trivial. D, E, F. So this is a lemma of Serre. Suppose P is a projective module. I don't care if it's finite. Suppose P is a projective module with a finite free resolution. I mean, finite length free resolution. So that will look like I have P surjected onto by some free module, whose kernel is surjected onto by some free module, and so on. And at the last step, I have a free module. then P plus the sum of the odd terms is isomorphic to the sum of the even terms. In particular, I have P plus a free module is isomorphic to a free module. And if everything was finitely generated, this has a rank. So does this. And this locally has a rank by this. I can localize at the primes and find the rank so that the ranks will add up. EF. And finally, one last, I should have put this with the commutative algebra. So this was kind of homological stuff, and then there's one more commutative algebra fact. So this is a lemma of Nagata. For some historical reasons, a lot of commutative algebra was developed by Japanese people in the first half of the 20th century, also Germans. It's kind of like the fascist society for commutative algebra. It was awesome. Okay. So if A is a domain, F in a prime element, so the ideal generated by F is prime. I think I should, so part of it will need Noetherian. So let me just put in Noetherian anyway. Then for all primes P not containing F, so those are exactly the ones that localize to primes in the localization. The localized prime, so let me call that P tilde in A tilde, which is the localization where I invert powers of F. So the claim is if the localized prime is principal, may or may not be. But if it is, then the original prime is. Okay, and so since, so there's a conclusion of this. So since the codimension 1 primes in A are of two types. So since the codimension 1 primes in the original A, there are two types. There's either F itself, the ideal generated by F, it was a prime element, or they're the other ones, which don't contain F. Those are the only possibilities. So since the codimension 1 primes in A are either F or a P not containing F, this means that if this localization is factorial, if it's factorial, then this other fact over here says that happens if and only if all the codimension 1 primes are principal. So if this is factorial, all its codimension 1 primes are principal. Therefore, by this lemma, they were actually already principal in A. Therefore, A is factorial. So if the localization is factorial, then A itself is factorial. Okay, so that's everything we need. These are the facts we need. If you knew lots of commutative algebra, you would already know these facts, and I could just give you the proof. So let's pretend we know these facts, give the proof, and then come back and see how many we can prove before the end of the lecture. Okay, so I have 2 boards to work with, and I don't want to erase my facts because I'll refer back to them. So if I start erasing any facts, accidentally warn me. Okay, what do we have? Okay, so let me state the theorem and we'll do the proof. So theorem. I think this is also Auslander Buchsbaum, but I'm not sure. So regular local rings in the definition, these things are Noetherian. Regular local rings are factorial. So the proof will involve induction on the curl dimension. So let A be a regular local ring. So all these quantities like the curl dimension, the depth, the projective dimension, the number of minimal generators, they're all the same. We know this now. In particular, it's of finite projective dimension. And we're going to induct on the curl dimension. So let's consider dimension 0. So if dimension of A is 0, then m mod m squared is 0, because the dimension of that is 0. And that means, what is m mod m squared? It's m tensor A mod m. And so by the Nakayama lemma, this means that m itself is 0. But in a commutative ring, the 0 is a maximal ideal if only if the ring is a field. So A is a field. Hence, factorial. Everything's a unit there, so all of the factorizations are trivial. Okay, so now let's suppose we've proved the theorem up to some curl dimension. So now suppose we know the theorem up to curl dimension, let's say n minus 1. Okay, so now, and assume we, in curl dimension n, we're going to reduce. So assume dimension of A equals n. And ultimately, we're going to apply this characterization of factorial that we want to check that every codimension 1 prime is principal. This is what we need to show. And we're going to use this Nagata lemma to reduce this to a question about a localization, a certain localization which will be of lower dimension. And this will get us going. So in order to introduce some prime element f, consider an element f which is an m but not an m squared. Then I claim that it's a prime element, so that we'll be able to apply this Nagata lemma. So note, so then A mod this element f, we showed that if I took something in M but not in M squared, when I took the quotient by it, it remained a regular local ring. So then this is, again, regular local. In fact, we showed more, right? That if you took a quotient by a regular sequence, it remained a regular local ring. So this is, again, regular local, hence a domain. I showed that regular local rings are always domains. But now I took a quotient by an element of the ring. I got a domain. Therefore, that element must have been prime. It generates a prime ideal. That's the only way the quotient could be a domain. So f is a prime element. So now I have my prime element. So by the Nagata lemma, it's enough to see that A invert F is factorial. This will imply A is factorial. And so we're going to study codimension 1 primes in this localization. So let's check. We need to check codimension 1 primes here are principal. That is, they're free of rank 1 as modules. Since we're in a domain, being principal is the same as being free of rank 1 as a module. Because it's the image of multiplication by F, which is an injection. So now consider a maximal ideal. So consider, let me call this ring, so I don't have to keep rewriting it. Let's call it A prime. And now consider a maximal ideal. P prime in A 1 over F. In A prime, A 1 over F. And note, just so you don't get confused, we started with something which was a local ring, but once we inverted F, it no longer has to have a unique maximal ideal. F was in M, so when I invert F, I'm inverting something in M, and it just becomes equal to the whole ring. So I lose the maximal ideal M, and then I have all of the other primes that were lower than it. So I no longer have a unique maximal ideal. Nonetheless, it's a localization, so it's still finite homological dimension. So consider a maximal ideal prime. Then consider the localization of A prime at P prime. And this will be the same as the localization of A at P, where P is the prime that localizes to P prime. So it's some prime. So these are both A1 over F and these localizations at these primes. They're both of finite homological dimension, since that's preserved under localization by whatever the fact was. It's fact C. So then these are A prime localized at P prime, same as A localized at P. These have as finite homological dimension. Since it's the localization of such. And so by the theorem characterizing regular local rings, this is a local ring of finite homological dimension. It is itself regular local. So A prime at P prime is regular local by the big theorem. By our big theorem from last time. On the other hand, A prime P prime also has strictly smaller dimension than A. Because in this localization, we lost the maximal ideal. We inverted something that was in the maximal ideal, namely F. So by induction, this is factorial. A prime at P prime is factorial. Which means, for all codimension 1 primes, Q prime in A prime, I don't yet know anything about it in A prime, but I know that when I localize it at P prime, it must become principal. Q prime localized at P prime becomes principal. So it's free of rank 1 as a module. But now, if I fixed Q prime, I could have done this for any P prime. Fix Q prime in A prime. Go over all maximal ideals. P prime, localize, I get something which is free. Therefore, Q prime must have been projective. So since all localizations of Q prime at maximal ideals are free of rank 1, Q prime itself is projective as an A prime module. By this characterization of finitely generated projective modules in terms of the localizations being free. Okay, good. But whatever Q prime is the localization of some Q in A. Actually, maybe I don't even need this. Hold on. So I have A prime. Yeah, no, this is fine. So I know that A prime is finite homological dimension. Therefore, everything has a finite length resolution by freeze. So since A prime is finite homological dimension, since it's a localization of something of finite homological dimension, Q prime has a finite free resolution. And now it's finite length and finitely generated because we're in a Noetherian setting. So it has a finite free resolution. So by Serre's lemma, I have Q prime plus some free thing of some rank, say n minus 1. And the ranks differ exactly by 1 because I know that when I localize, I get something of rank 1 here. Okay, so by Serre's lemma, I have this. And so by the other lemma on the summons, that was what? Fact E. So by fact E, Q prime is isomorphic to A prime as a module. It's not equal, it's just isomorphic as a module. And so it's free of rank 1, so it must be a principal ideal inside of A prime. So thus, Q prime, which was any codimension 1 prime, is principal. So A prime which is a over 1 over f, is factorial, since this was true for any codimension 1 prime. So by the Nagata lemma, which is what? It's fact G A is factorial. Okay, so there it is. This is the proof. This is the proof as presented in the book of Eisenbud on commutative algebra. In Weibel, he doesn't give the proof. He just gives a reference to some book of Kaplansky, which I've never looked at. But I suspect the proof there is very similar. I think this is probably close to the original proof of Auslander-Buchsbaum, but I'm not sure about the history. I've heard that Dennis Gatescory recently found a more purely homological proof, which, I don't know, has some conceptual advantages, but I haven't seen it yet. So maybe there's a new, more clever proof, but I think this is the classical proof. And all proofs of these kinds of facts, I think, use these homological theorems. This is not something that is kind of practical to prove by purely studying elements and products of elements in a commutative ring. Okay, there we go. That's the proof. And how much time do we have to prove some of these facts? Another half hour? Okay, so let's see. What can we do? So let's try C, E, and F. D requires knowing an additional fact that I didn't write out explicitly. See how far we get. So let's look at proofs of the facts we used. So let's start with C. I said it aloud, but let's spell it out. Right. So at least we'll sketch. So suppose A has finite homological dimension. And consider a S inverse A module M. Take a finite resolution of it as an A module. Let's say free resolution, a finite free resolution. Free is not so important, but it's maybe more obvious that this will work. Finite length free resolution over A. So I don't know yet that this exists over S inverse A. So that will look like M surjected onto by some free module F naught. The kernel of that map will be surjected onto by some free module F1 all the way up to Fn. And after that, that injected. So this thing is exact. And now I'm going to localize each of these terms. And a free module, it looks like a sum of a bunch of modules A. So if I localize, that will be a sum of S inverse A's. So they obviously localize again to free modules. Actually, even if they were projective, they would localize to projective modules. That's slightly less obvious. But I also need to know that when I do this, the result is still exact. So let's call this star. So I want to apply, what is localization? it amounts to tensoring with the ring S inverse A over A. I think that I think we checked this in the seminar when we introduced localization. So, so 2 star. We'll get a complex which looks like this. Nothing will happen to M itself because it was already a module over S inverse A, where these guys are free S inverse A modules. And we need to check that the result is exact. If it's exact, now we have our finite length free resolution of M as an S inverse A module. And the basic fact is that localization is always exact, is an exact functor. And the way you show this is you show that as an A module, this localization S inverse A is a filter colimit of copies of A. So you check this fact by saying that S inverse of A is a filtered colimit of copies of A along some maps corresponding to the things that you're inverting. And so the tensor product commutes with colimits. And filter colimits of complexes are exact. So that's something that was shown in the first problem sheet. We were studying filtered colimits, and we showed that cohomology of the filter colimit was the filter colimit of cohomology. Okay, so this is some detail that we can fill in the seminar using stuff that we already know. By the way, this factor that localization is flat or exact is a very important fact. Okay, did I erase any facts? No. So that was fact C. Let's try now fact E. So fact E, suppose I have an isomorphism like this. So given an isomorphism of M plus A n minus 1 copies isomorphic to n copies of A, we're going to take wedge powers of both sides. So take wedge to the n on both sides. On the right-hand side, if I take the top wedge power of a free module, I just get the free module of rank 1. So on the left-hand side, you can check that what you get is, just a second, this will be m n copy, wedge n of an minus 1 plus wedge 2, sorry, it's a kind of like a binomial theorem kind of thing. So you need to check that this is what you get. You'll get wedge n on one copy, and then you'll get one copy of m and n minus 1 wedge n copies. Plus wedge 2 m wedge n minus 2, and so on. To wedge n m. And on the right-hand side, you'll get wedge n of a plus n is just a. So the left-hand side now is isomorphic to the right-hand side. This term, of course, is 0. This term here is isomorphic to m because wedge n minus 1 of a plus n minus 1 is a. And so I have some non-zero term here, and the other terms must vanish. Because there's a single sum in here. Is this what I want to say? Just a minute. So the way I stated it, I didn't need to assume that m was projective. It would be easier if m is projective. Let me double check what the general fact is. Very good. Yeah, okay, I do need to do something. So because of this isomorphism, yes, it's a summand of a free module, so it is projective. And moreover, if I localize at some prime, I get an isomorphism there. But when I localize at a prime, I get a local ring. And so every projective module is free, and so this will be a rank 1. So notice that MP is free of rank 1 for all primes P. And so the higher wedge powers of M will vanish. Because they will vanish in the localization. So if all the localizations of some modular are 0, then that module is 0. Okay, so this gives that m, the only non-zero term on the left-hand side is m, and so m must be isomorphic to A. Okay. So that's the proof of E. And let's look at this fact F. We start with a finite length resolution of some projective module, and then we want to split everything off and write the projective module plus a free module equals some other free module. So suppose F0, F1, and so on up to Fn is a finite length free resolution. So now we're going to do this splitting inductively. So F0 surjects onto P, which is projective. By the lifting property for a projective module, I can split that surjection. So since P is projective, there's a splitting of F0 as the image of F1 plus P. Just choose any splitting, and then the complement will be F1 prime, which will be isomorphic to the image of F1. Now, this image, F1 prime, therefore, is itself projective, because it's a summand of a free module. So then, F1 prime is projective, being a summand in a free module. And it's surjected onto F1, so I can split that surjection and then continue inductively. So then split the surjection from F1 onto F1 prime to get that F1 prime, sorry, F1 is a sum F2 prime plus F1 prime, where F2 prime is the image of F2. Of the map F2 to F1. Okay, so inductively, proceeding like this, now this F2 prime is again projective. I can split the surjection from F2 and so on. So inductively, we get Fk is Fk plus 1 prime plus Fk prime. Okay, and now if you just gather terms, want to do this. So now let's gather terms. And maybe it helps to do an example. Like fix the length. Let's say, just to be explicit, say n equals 2. So there's f0, f1, f2. So I'll have f0 is p plus f1 prime. f1 is f2 prime plus f1 prime. And f2 is f2 prime. Okay. Then if I look at p plus odd, I rewrite that using this decomposition. This is p plus f1 prime plus f2 prime. And now I regather this. P plus f1 prime is f0, and f2 prime is f2. So that's the sum here of the even terms, and on the left it's p plus the odd terms. Okay, and I just did a short example, but you can see that this will work inductively. Okay, so that was fact F, this observation of Serre. And we probably still have a little time. Yeah, we have 10 minutes, right? Okay, so we can say something about part D. So part D, we want to see that projective modules are characterized by the localizations being free. And one direction, 1 implies 2 implies 3, this will be easy. It's 3 implies 1, which takes a little bit of care. So let's suppose M is finitely generated over a Noetherian ring. And suppose M is projective. Then let's consider a localization. So a localization at a prime can be computed as localize the ring and tensor up to that localized ring. But if I take any projective module and induce it along a homomorphism, it remains projective by adjunction. We've made this observation before. So since projective modules induced to projective modules MP is projective over the local ring it's finitely generated projective over the local ring AP, and we know that finitely generated projective modules over a local ring are in fact free. That was a Nakayama type argument that we made before. So MP, in fact, is free of finite rank. Thus, the first hypothesis that M is projective implies that the localizations at all primes are free, and a fortiori, the localizations at maximal ideals are free. And so now we want the converse. We want to know if all of the localizations at maximal ideals are free. then in fact the module is projective. And for this, I'm looking at my notes and I got more advertisements for zombie games. Da, da, da. So I want to use a fact about localization of x, and I want to make sure I get the hypothesis correct. I don't want to state more than is true. Yeah, okay. Right. Okay, so now we need the converse. So now, suppose that the localization NP is free for all maximal P. I'll claim now that M is projective. Now, one way to check projective is to check that X1 from that module into any other module is 0. That's the X'd characterization of projective. And that's what we'll use because X behaves well with respect to localizations. And that's because projective resolutions behave well with respect to localizations. So then, consider the following. Any other module, n, we're going to show that x1 into it vanishes. So consider any other module, then I could take x1 from M into N. That's a new A module, so I can also localize that at B. And you can check, because of the behavior of localizations, because the behavior of free resolutions, say in M with respect to localization, this will be x1 over the localized ring from the localized module into the localized module. So we can double check this in the seminar, but it's just the fact that free resolutions localize well. Then this is 0 because MP is free. So this is for all maximal ideals P. This x1 vanishes. The localization of the x1 vanishes since MP is free. And now it's a general fact that if I have a module whose localizations at all maximal ideals are 0, that module itself is 0. So x1 itself is 0. Since localization all maximal ideals is 0. So you can check whether or not a module is 0 by these localizations. Hence, M is 0 because it has no x into any other module. Okay, so that's the proof. And then in the seminar, maybe we can give some more details wherever you like. And in particular of these purely commutative algebraic facts, which are pretty straightforward, but it's worth thinking them through. I took some minutes to think them through when preparing my lecture. Okay, so that's it. I hope you enjoyed the course. For those of you not graduating this year, you have a few weeks to write solutions. If you have more questions, write to me. So that's all.